The first video for Unit 9 is reaction rates and kinetics. And I'm just going to introduce to you a little bit about what both these terms are and how we look at a reaction in a new way in this unit. Before, we've looked at predicting the products of reactions, we've looked at the types of reactions, we've looked a little bit at redox reactions. What we haven't really gotten into is how a reaction is able to happen at all and what kind of energy it takes to have that happen and what sort of things we can adjust to make the reaction go forward. So if we're trying to take reactants and turn them into products, what sort of things can we adjust in the reaction in order for it to go forward most efficiently and to give us the most product that we can get in a given amount of time, or with a given amount of heat or pressure or whatever system stress we might put on the reaction and make it do that. Kinetics just has to do basically with the energy associated with the reaction. And that has to do sometimes at the smallest level with how the atoms and molecules are interacting with each other. The reaction rate is something that we'll look at with a sort of a basic generic reaction template here as our guide. So I have here basically just a simple reaction, A plus B yield C plus D. Now we're not concerned about what kind of reaction this is or what A, B, C, and D are. For now we're just concerned that A and B are reactants. They're going to turn into or yield the products C and D. When we have a reaction like that, we can balance the equation, we can take it and use it to do stoichiometry. And we often just typically assume that these reactions will just happen no matter what. If I can write the equation and balance it, well, then it would just happen. We know that's not always the case because things like the activity series tell us that certain reactions can't happen. But we often assume that reactions in general, if they're not maybe an activity series reaction, will just happen. When in fact there are lots of reactions that don't just happen, and some are impossible altogether, or energy just isn't there, or the energy doesn't make sense in the reaction for it to occur. So I'm going to tell you a little bit about, have you kind of think a little bit about the three kind of things that must occur, must be true, before a reaction will actually happen between A and B. What three things must be true before A plus B will yield C plus D? That's basically the idea. And some of these are real no-brainers. Other ones maybe have to make you think a little bit. So for A and B to yield C and D, just a real basic truths. One, you've got to have A and B present. So whatever A and B are, you have to have both of those two substances. Just because I can write the equation doesn't mean I can do the reaction. I actually have to have A and B in bottles or containers or samples of some kind so that I can put those together. Second thing that has to happen is the particles of A and B have to collide with each other. And collide sounds rather violent, and really at the atomic level it kind of is. The two atoms or molecules or formal units, the ions, A and B, those particles must bump into each other, run into each other, and we call those collisions in chemistry and kinetics. And that's really where kinetics gets into things. We think about kinetic energy as the energy of movement. Well, here we have particles moving, and they collide with each other, and they have enough energy at times for a reaction to occur. And that's our third sort of requirement, is that the collisions between A and B have to be strong enough or powerful enough in order for A and B's bonds to break or form or change or rearrange in some way to give us C and D. The atoms involved in A and B have to rearrange or recombine into something else. If they don't have enough energy to do that, you won't have the reaction cause A and B to turn into something new. They'll just bump into each other and then continue on about their business. I think a lot about the case of if you're driving and pulling into park somewhere, maybe you back into parallel park between two cars, and as you're backing up, you might get a little too close to the car behind you, maybe you tap the bumper. Well, it's kind of what bumpers are meant for on cars, is for cars to be able to bump into each other like that at low speeds and not damage each other. And so when you bump into a car at low speed in your car, you're not going to damage the other car, you won't have any damage yourself, you might not even scrape the paint at all or have any kind of a mark, because cars are built to withstand some low energy collisions. But when you get high enough energy collisions, of course, they get damaged and cracked and dented, and you have to rebuild them, and it's quite expensive. But cars are built to withstand certain collisions without a damaging result to your car's body or bumper or whatever. So the same thing is true in chemistry. When we're looking at how A and B will react with each other, sometimes there isn't enough energy in the collisions between A and B for the reaction to actually happen. And you'll be left with A and B unchanged just as they were before, just like those two cars bumping into each other in the parking lot. What I'm going to have you fill out and add a little bit of labeling to basically on a reaction kinetics diagram are some terms and locations along this curve that have to do with the energy involved in the before and the after, or in the reactants and the products, and in some of the energy that's required to get from reactants to products. So what you'll see on one side of your page, and be careful you're looking at the right one because the two images look very similar, but make sure you're looking at the one that looks like this. It starts a little bit on the left side higher and ends a little bit lower on the right side. So it starts higher up on the hill and ends up lower. This particular reaction has two curves. On my screen, they're sort of blue and red. The top one is somewhat red, the bottom one is somewhat more blue. But it's sort of a higher hill, if you will, and a little more gentle or lower hill. What we're going to do is label several locations along this curve and show you what it represents. Then we're going to talk about some of these little differences and those little arrows that you see marked off to the right there as well. So notice the axes. This is a good way to look at any graph at all, right? Just to see what are on the axes here. Well, my x-axis is more or less time. Reaction progress means time is progressing. Starting from the beginning to the end, time is passing. Might be seconds, might be hours, might be days. But every reaction takes time. And on the y-axis, we've got energy. Energy, then, from low up to high, the energy here is what we would consider chemical energy. The energy that's stored away in the bonds of a substance, held but in the atoms, how they're bonded together. There's energy stored in those bonds, and that's the energy that's released when you eat food, for example, and that breaks out of the bonds in the proteins or carbohydrates or fats that you're eating, and it becomes the fuel for your body's processes. So this is that chemical energy that's stored in substances, and it can also be heat energy, all put together. So total energy on the y-axis. What I want you to label first is the initial energy of the reactants. And this is basically at the very, very left edge, the very extreme before. The earliest moment on the graph is what we consider the initial energy of the reactants. And then along comes the curve that connects us to the end. So on the other end of the graph is the ending energy of the products. We start out at a certain amount of energy, in this case, and we drop down to less. But we go through a particular path along the way, and there's energy associated with that. The little arrow that I'm pointing you to here on the far right side shows the difference in energy between the reactants and products. So we start up a little higher, end down a little bit lower, and this difference then that we can look at a graph and estimate that value is the difference in energy that's stored in the reactants and products. In this case, the reactants have more energy stored because they start up a little bit higher in energy, and by the end you've gotten down a little bit further lower in energy. Now what we're going to do next is look at and kind of describe what that means to us when energy is being lost, or when energy is changing. Is it being lost or being gained? And in this case, it's being lost because we start out with more energy and end up with less. So in this case, because the reactants have more energy stored than the products, this reaction would be considered to be releasing energy. And often that's released as heat. Sometimes it's released as light, but generally we'll see it most often as a reaction releasing heat. And we would consider this reaction then exothermic, which is a term we've mentioned before. When heat is released by something, it's considered exothermic. And so this particular reaction on this side of your page would be considered an exothermic reaction. Now, for every reaction to occur, a certain amount of energy is needed, and that amount of energy is known as the activation energy. You see that here abbreviated as capital E, little a, the activation energy, energy of activation. Basically, the idea is that as you add energy to the reactants, they gain energy, they sort of become energized, and if they have sufficient energy, they can get to a sort of a tipping point. In other words, we call it here the activated complex. It's the intermediate moment, sort of that deciding moment of truth. Is the reaction going to turn into products, or is it going to return to its reactants and not be changed at all? So you're sort of at this tipping point. It's almost cartoonish to think about sort of moving a heavy object up a hill, and you get at the top and it kind of teeters there. Is it going to fall back to the beginning, or is it going to tip forward and fall to the other side? In our reactions, it's the same idea. Here you've got a goofy little cartoon of a fellow pushing a large boulder up a hill. He gets to the top of the hill with that boulder, and you can see it labeled there as the tipping point, and he gives it perhaps a little kick with his foot, and down the other side it goes. Every reaction has a tipping point like that, where some of the particles will return to the original, and some will continue on to the end. Here's another cartoon of a guy rolling a ball, or a rather big boulder up a hill. But this one, the curve and the hill, look a little bit more like the curve that we are looking at. We start out with a high point on a hill, we go up over a steep slope, and then it goes down to the end. So from A to B is kind of like our reactants to products on our graph. This graph and this graph, fairly similar. The next thing to label, I'd like you to label, is this tall arrow to the right. This is the activation energy, the amount of energy needed for the reaction to occur. In this case, we're talking about the forward reaction. A forward reaction means we're starting from reactants on the left and considering those all the way through to products on the right. So activation energy is the amount of energy needed to go from the beginning, the reactants, to the products, which would be over here at the end, okay, via the red curve, the red line, or my top line on your page if the colors aren't showing up right for you. So it's going through the top or steeper, more difficult looking slope. And that amount of energy then, shown as the arrow from the peak of that hill down to where the hill begins, this large amount then would be considered the activation energy of the forward reaction, because you're going from left to the top of the hill and then down the slope, okay? But not using any kind of a catalyst. Now we haven't defined what the heck a catalyst is again to go with kinetics here, but when you don't use catalyst, it takes more energy. And this lower energy curve is the activation energy of the forward reaction, again, going from left to the top of the smaller hill and on through to the products. Means you have to go over a hill this size, this little arrow's size. Activation energy of the forward reaction with a catalyst being used. So a catalyst then is a substance that allows a reaction to happen at lower temperature, at lower energy conditions, and usually the reaction then will be a lot faster because you don't have to heat it as much for it to occur. A catalyst basically takes the activation energy, which is originally this taller hill, and it reduces the size of the hill down to something quite a bit less. And of course that makes the reaction more possible because you don't have to add enough energy to go all the way up to the top of this peak. You only have to add enough energy to go to the top of this peak, and perhaps that's easy, and a reaction will become more natural and spontaneous of its own. On the other side of the same page, you'll find a graphic that looks very similar in a lot of ways. Same x and y axes, same kind of look with two curves, two different paths to go from left to right, and some arrows and things that we'll label to talk about the energy associated with this reaction. But notice the biggest difference here is that you start from a low energy position on the left, you go up through one of the two curves or one of the two paths, and you end up at the products at the right hand side, but those products are at a much higher energy position. So you actually started from a low energy position and you increased your energy to a higher energy position. The initial energy of the reactants then is a very small, well, not very small, but a smaller amount. And so we started a low energy spot by comparison, and by the end the products have more energy of some amount. They've gained overall a net gain. They've taken in extra energy and have stored it away in their bonds and so forth. So this is the kind of reaction by which you start with low energy things. You add heat to them, perhaps sunlight, perhaps energy from a Bunsen burner, who knows what it might be. And that energy, at least some of it, gets stored away in the chemicals in the reaction equation. You can think about like photosynthesis in plants, right? They take low energy things, they bind them together into much higher energy products, and at the end we have sugars or starches being made perhaps by a plant that has those sugars and starches have more energy in them than did the original ingredients, water, carbon dioxide, and so forth, as we look at the basic photosynthesis reaction. So how much more energy is in the products than in the beginning? Well, you can see there's an arrow here labeling, just like there was in the other graph, the labeling the change between reactants and products. In this case, the arrow starts lower and goes higher, so this would be a positive difference between the reactants and products. If I started out at 100 and ended at 200, that's an overall positive gain of 100 units of energy, and we'll talk more about the units later on. So that first arrow on the very left shows the difference in energy between the reactants and products. Now, because this reaction goes up, it starts low and goes high, it's just the opposite of our last example. In this case, we start with low energy, that energy is absorbed to add to that, and we end up higher up. So this reaction would be considered to be absorbing or taking in energy overall. And that in many circles that would make it an endothermic reaction. It's taking in energy, and in the end more is found stored in the products, almost like you've charged a battery by carrying out this reaction. And again, we call that endothermic. Endothermic meaning heat energy is going inward to the reaction and being stored away. A couple other things to label on this graphic, then we'll be all done with this video. The biggest arrow on either side is this one right here. This is showing how much energy is needed to go from the reactant side on the very far left up through the highest peak, okay, and then down to the finishing point. This is the sort of example of starting very, very low at the bottom of the valley on this little hill diagram and having to go to the tip top of a big mountain before going down the other side. That's a long hill, a long haul. That forward reaction, if it's going through the non-catalyzed, we say, path, that's the one that goes up and over the heavy, steep direction and over the more difficult paths, okay, across this mountain, if you will. The activation energy of the forward reaction, because we're starting at the beginning of the curve, going up through the hill to its peak, whatever that peak might be, and then coming down to where the reaction stops. If you go through the lower curve, if you're going through the lower pathway here, then it's going to take less energy overall. And that the cause of that then is that one contains the catalyst. The activation energy is reduced. It takes less energy to clear that hurdle. It takes less energy to cause a reaction. And because of that less energy, the temperature doesn't have to be raised perhaps as much, but the reaction certainly will go faster. Because less energy will mean that the reaction can go on less fuel, and you can make your reaction go longer than before or faster than before with the same amount of energy perhaps, or you can make it speed up by adding energy, and it'll have a much more dramatic change than it used to have. Catalyst, again, all the catalyst can do is reduce the activation energy. It can only get it so low. It can't make that sort of a little dip instead of a hill. If that was going to be a hill of some size, but a catalyst can really, really reduce the activation energy successfully and make a reaction go a lot more quickly. So because the reaction in this case would have to still go uphill to go from left to right, no matter how much you make that hill, in this case, shorter by shortening it up from the steepest mountain here down to a much smaller one, you're still having to add in some amount of energy to get over even a small hill there because you're starting down a low position. The catalyst can't get rid of the fact that you're starting out in the valley and ending up here above on the plateau. So you're going to have to go uphill at least a little bit, even if the catalyst is really, really good. That's it for kinetics and our initial diagrams. Next, we'll get into some things that have to do with the things that actually affect reaction rate, what we can do to cause changes in reaction rate, and what that looks like as far as examples in real life relationships to things you already know.